Today we're happy to have Spencer Leslie from Duke, and he's going to tell us on the modular forms of half-weights with exceptional groups.
All right, thank you, Jingwei, for the invitation and the introduction. I apologize for doing this on Zoom. I've been having childcare issues, so travel was sort of out of the question at this point, but I'm really happy to be here, and I thank you all for coming. So as mentioned, I wanted to talk about some joint work with Aaron Pollack, developing a theory of modular forms of half-integral weight on exceptional groups. And so the point here is to maybe combine two different areas of research in automorphic forms, namely the study of certain special automorphic forms on exceptional groups, which go by the name modular forms and have very nice arithmetic and Fourier theoretic properties, with the theory of metaplectic groups on these exceptional groups to sort of come up with new interesting examples. And so to start off, I'm going to begin with a sort of motivational warm-up. Which simultaneously wants to recall modular forms of half-integral weight on the upper half plane. So the first example of such a thing is Jacobi's theta function, which is also more or less how you get the theory off the ground. So we take just the classical theta function, squared, and the point here, and z here is in the upper half plane. So the point here is that this gives an example of a modular form of half-integral weight. What do I mean by that? Well, I mean that, so I need some level. So just for simplicity, I'll work with a slightly smaller level group. So I'll take gamma to be some element in gamma 1 of 4, so congruent to modulo 4. And I'll define, I'll write j1/2 gamma of z to just be the quotient of gamma acting on z, fine, divided by theta of z. So what does it mean for this to be a modular form of half-integral weights? It's just referring to the fact that when gamma is in the subgroup, then this function satisfies the property that when I square it, so first of all, this is a holomorphic function, but when I square it, I get the standard multiplier system for a weight 1 form. Okay, and so it's meaningful to refer to this as a modular form of half-integral weight. And so once you have this multiplier system for level gamma 1 of 4, you can then develop a whole theory of modular forms of half-integral weight, and that is essentially the starting point for what Shimura does. And this produces a lot of very important classical examples of automorphic form. Just to give a motivational example, I'm going to do something rather simplistic. I'll call this thing C sub CZ. I'm thinking of C and Z referred to Cohen and Zagier because they study a Mach modular object related to what I'm about to write down. So I'm just going to take Jacobi's theta function and cube it. And the point here is that it's pretty easy to see what the Fourier coefficients of this thing are. They're just going to be the representation numbers. So namely, the number of ways that I can write in as a sum of 3 squares. Okay, so we have a example. So this thing, I took a weight 1/2 guy and cubed it. So this is weight 3/2. And its Fourier coefficients encode these representation numbers, which are already interesting enough. But in fact, these are related to class numbers, for example, using the following theorem of Gauss. So I'll just, I won't state the general formula, so I'll just take some specific n. So for n greater than or equal to 4, let's say square free. and congruence to 1, 2, 5, or 6 mod 8, then these representation numbers, so these Fourier coefficients, are 12 times the class number of the associated imaginary quadratic extension. Okay, and so the point here is that we have an example of a modular form of half integral weight, and the Fourier coefficients are very interesting arithmetically, namely you get these class numbers showing up. And so maybe from so this, I've punted to a theorem of Gauss in order to relate these Fourier coefficients, but as you might imagine, there's really just a class number formula floating around. So how might you construct this thing in a different way? A different perspective, which is related to the example I'll discuss in a second in our work, different perspective. So now I'll let H3 be the Siegel upper half space of 3 by 3 matrices. And I'll consider the following theta function. So maybe I'll write this as theta 3, because this is going to be a Siegel modular form of half integral weights, so on SP6. So what is this? Take Z, I'll sum over the lattice Z cubed, e to the 2 pi I, V, Z, V transpose. Okay, then this gives me a modular form. As I said, it's a modular form of half integral weights, so it's a Siegel modular form of weight 1/2. And I can use the following embedding of I have the following embedding of the complex upper half plane into the Siegel upper half space just by taking a complex number Z to the diagonal matrix Z, Z, Z. And it's easy to see that this Cohen-Zagier modular form that I wrote down here is just given by taking the restriction of this modular form on the Siegel upper half space and pulling it back to the embedded copy of the complex upper half plane. Okay, so why does this say anything? Well, now I'm not going to say anything more about this, but just the point is that you can use a Siegel-Weil theorem to relate this theta function to an Eisenstein series. And then these class numbers will arise from a class number formula for appropriate Dirichlet L functions sitting in the Fourier coefficients of this Eisenstein series. Okay. So the point I wanted to say is that you get this example of a modular form of half integral weights, but really it's somehow coming from L functions. So now we're going to do something very similar. So this, let me sort of say what our work is. So what's our work? So what we're going to do, and I'll sketch this throughout the talk, we develop a theory of modular forms of half integral weight on exceptional groups, but really for the sake of this talk, we're really just going to talk about G2 and F4, but we also deal with other groups as well. And then we construct a specific example, a weight 1/2 form on F4, and then use this to prove the following theorem. So our main theorem, so I'm going to say it, well, I'll say a part of it just because it's going to, the full thing would take a bit more notation. So the statement is that there exists a modular form of weight 1/2 on G2. So let's call this thing theta of G2. So as I'll explain, the Fourier coefficients of these modular forms on G2, so these are Fourier coefficients, are parameterized by binary cubics. So if I have a binary cubic polynomial, so let's say let's say with z coefficients, a cubed plus b u squared v plus c u v squared plus d v cubed, then I can associate the following cubic ring. So I'll let R be z y mod this polynomial, say evaluated at y1. Okay, and so these are the Fourier coefficients are in general parameterized by these binary cubics. So similar to what happens for the thing on the 3/2 guy we saw before, there's in general something that's rather complicated, but for certain Fourier coefficients, we get something rather nice. So I'll explain what this means later, but I'll say for P such that R P is even monogenic, the P Fourier coefficient of theta G2 is equal to, so I'm going to say a sign here that I'll explain later on. So this is 24 times the size of the 2 torsion of the narrow class group. So part of the definition here is that this is maximal in its field of fractions. So this makes sense. Okay, so the narrow class group of this field E times the number of totally positive units modulo squares. Okay. So we get this Fourier, this modular form on G2 of weight 1/2 with these arithmetically rich Fourier coefficients. So this is sort of our main result. And as I said, I'll explain a little bit about what's going on here. An interesting point I want to just point out is that our theory does not, we're not actually going to use a Ziegel-Vey type formula in order to get these class numbers. So we have these 2 torsions of narrow class numbers. So it's not clear how this would be related to a, or at least not clear to me, how this would be related to some special value of an L function. But in particular, that's not our approach. We actually do some arithmetic invariant theoretic arguments in order to get these Fourier coefficients. Okay, so what I'm going to do now is I'm going to explain what I mean by modular form on G2, and then I'll introduce the half integral weight theory before I get to the proof of this result, which I hopefully will have time towards the end of the talk. But before I do that, let me just really quickly, so maybe section 1.5, relate these modular forms to the metaplectic group, because that's what we're going to need to do on the exceptional group case. So recall my weight 3/2 modular form on the upper half plane. So what I want to do is I want to relate this to an automorphic function on SL2. So relate, want to associate this to an automorphic form on SL2R, as one naturally does. And the problem is you can't do this. And so this is where the metaplectic group comes in. So just naively, what you would do to imitate what happens for the integral weight case is, well, this is weight 3/2. So I would take the standard multiplier. Let's see, sorry, I wanted to write G, where G is in SL2R, J, I, -3 halves E C Z G acting on I. And that would give me my function. And this is how you define the associated automorphic form if you have an integral weight thing. But the problem is this doesn't make sense. And so what you do instead is you just develop a group that has all the possible square roots of this multiplier system in the definition. So now we define SL2 tilde to be the set of pairs G, J, G, where G is an SL2R, and JG is a holomorphic function on the upper half plane such that it squares to this multiplier of weight 1/2. So here, A, B, C, D. Okay, so you just include all the relevant square roots of this thing into the definition, and now we have a good notion. So what we do is instead we erase this nonsense and we write G, JG of JGI -3. And that gives me now a automorphic form of on this covering group. So the fact is that this is a double cover. So the surjection, or so the map to SL2R is surjective, and we have just a kernel mu2. And we can talk about automorphic forms because, as I mentioned, gamma 1 of 4 sits discretely in SL2R, but the theta multiplier gave us a splitting. Namely, it gave us a choice of how to give a square root of this multiplier. And so we can embed gamma 1 of 4 inside this, and now we have a good notion of an automorphic form on this covering group. And so I'm going to want to write down the properties of this form here, because it's going to come back when we just define things this way on the exceptional groups. So black. B, C, Z satisfies the following 4 properties. So it's first of moderate growth on the group. It's appropriately invariant with respect to gamma 1 of 4. So theta of gamma G is equal to theta of gamma, or sorry, of G, where gamma here is in the image of this splitting into this double cover. So to be precise, I should really be writing pairs here, but if there's any confusion, let me know. Also, it carries the character associated to the weight. So here I have the compact group SO2, and here I have the same compact group SO2. This is the maximal compact, and this associated quotient is just a squaring map. And so if I take an element in SO2 sitting as the maximal compact of this cover, it's equivariant with respect to the character theta B of G, where theta is the appropriate element of the circle group. And lastly, since it came from something which was holomorphic, I have that this satisfies some linear differential equation, just encoding the Cauchy-Riemann equations. Okay, so there's some linear differential operator here. So I apologize for going through just the definition here, but the point of writing this down is because this is exactly what we're going to define things as in a minute. Okay, so now that I've sort of explained how these half-integral weight guys correspond to automorphic forms on these metaplectic double covers, I'm going to talk about something a little different, just recalling the theory of modular forms on exceptional groups. And for simplicity, I'll just stick with G2. So this is the integral weight theory. Okay, so what we need first, so we're going to want to think about this in a semi-classical kind of language. So I need to consider the symmetric space associated to G2. So I'm thinking about G2, here's the split exceptional group. So I'm on it by its maximal compact. excuse me, which is isomorphic to 2 copies of SU2 mod plus or minus 1 in the center. Okay, so you know, the fact that there's a theory of holomorphic modular forms on the complex upper half plane is reflecting the fact that the locally symmetric space has a Hermitian structure. In this case, we have no Hermitian structure. But what we do have is something a bit more sophisticated. Well, I guess it depends on your point of view. So going back to work of Gross and Wallach, they point out that this symmetric space has a, so this has XG2 has a quaternionic structure. And they use this, so use to construct a family of so-called quaternionic discrete series representations. So I'll just call this pi L, where L is some integer, actually positive integer. And the reason I mention these is that these in the context of G2 will play they'll play the role that the holomorphic discrete series play for classical modular forms. And so in that context, the character, the weight is encoding the minimal K type. So the minimal K type here, I need a representation of this K. It's what I'll call VL. So it's the symmetric 2L power of the standard representation on the first copy of SU2 and the trivial representation on the second. Okay, and so we're going to use this just like as sort of the motivation for the following definition for a modular form of weight L on the exceptional group G2. Definition. And I should say this, I guess, has its genesis in the work of Witek, Gan, Gross, and Savin, but I'm going to use the definition that was, I think, first written down by Aaron, which is just slightly more general. So a modular form of weight L, and I'll just, for the simplicity, I'll say level 1 for the entire talk, is a smooth function, C on G2, valued in this K type, satisfying precisely these rules. So why did I write these things down? So that I could do this. Not sure if this is a good idea. I didn't get all of them. So let's, oh no. Okay, fine. Well, that was a failed attempt to drag that down. So it satisfies precisely those 4 rules from before. So first, it's of moderate growth on the group G2. It satisfies the transformation law of automorphy. So gamma here is a point in G2 of Z. It's equivariant with respect to the K group, the maximal compact with values in this K type. And finally, we need a differential equation, which is encoding the fact that it arises from these holomorphic, or sorry, these quaternionic discrete series or analogous generalizations thereof. And so there's a particular linear differential operator known as the Schmidt operator that we need phi to be annihilated by. So linear differential equation. That's sort of playing the role of the Cauchy-Riemann equations in this case. Okay, so this is the definition that was given by Aaron, and the point is that it cuts out a particular family of, or a particular type of automorphic function on the group G2. Why would one be interested in these particular automorphic functions? Well, the point is that these possess strong, well, let me say they possess a robust theory of Fourier expansions, of Fourier coefficients. So in particular, we can associate a family of complex numbers to them. And surprisingly, maybe perhaps surprisingly to me, these Fourier coefficients appear to have strong arithmeticity properties. So what do I mean by this? Let me go ahead and recall this structure. So let me first, in order to say what these Fourier coefficients look like, so let's recall the root system for G2. I'm just going to draw the diagram. Okay, so here are my, here's the root diagram for G2. This corresponds to its Lie algebra. And on that Lie algebra, I can give the following three-term grading. I'm going to grade, so this is the one component, 0, and the negative 1. So this is a Z mod 3 grading on the Lie algebra. So Lie G2 corresponds to these roots. So this grading corresponds to a particular maximal parabolic of the G2. So namely, this 0 component is the corresponds to the Lie algebra of a levy, which is isomorphic to GL2. It's just the short root GL2. And in here corresponds to the nilpotent or the unipotent radical. And the important point here is that this is a Heisenberg group, right? These roots. So the Lie algebra here is spanned by these 5 vectors, and these 4 here. This one-dimensional space up here corresponds to the center. This is the Lie algebra of the center, which I'll name Z. And so in particular, if I take in and mod out by that center, I get a symplectic space. Okay. So why do I mention this? Well, the point is, it's with respect to this nilpotent, this unipotent radical that we're going to define Fourier coefficients. So if phi is a modular form, then I can take the constant term along Z. So this is just the Z of R mod Z of Z, Z of Z, G dz. And so now I've quotiented out, but I've taken the constant term with respect to Z, so I can Fourier expand with respect to this abelian quotient here. And so just tautologically, I get, well, okay, so there's a little bit of work that goes into this, but nothing hard is being said here, where these are the Fourier coefficients. Pair omega with the image of n in the quotient again. Okay, so this is just sort of structural, but the point here is that we're going to have a much tighter statement for these. In general, these are they're just functions on the group G, they still have automorphic properties with respect to the Levy subgroup, but in general, they're very complicated functions that it's unclear what all we can say. So note, I'll say the following. So I need one more definition. So if I take a vector in this space, W, so it's 4 integers, or real numbers, say, I can associate to this the following a binary cubic, which is precisely the one we saw in the main theorem earlier. So this is going to play a role in a second. We'll say that omega is positive semi-definite, and denote that by omega is greater than or equal to 0, if and only if. So I can use this function to write down a polynomial on the complex upper half plane, just by plugging in 1 for z. So we need this to be non-vanishing for z in the complex upper half plane. So this is just going to give me a sense of positivity, like positive integers in the Fourier coefficients for. So I'm recalling this because this is all in the integer weight case, and this was proved by Aaron. And the modular forms of half integral weight that I'll mention in the next section all satisfy the appropriate analogs of this expansion. So we have the same sort of general structure. So there's 2 statements that I'll give. So if so basically the negative Fourier coefficients vanish. So if it's not positive semi-definite, then we can throw these guys out. They vanish. So phi here is a modular form. Let's see, modular form on G2 of weight L and level 1. And so what's interesting here is when I have these positive semi-definite guys, these are all, these can somehow be uniformly expressed. So there exists an explicit function, which I'll call W omega L, such that this Fourier coefficient of phi is equal to a constant multiple of this function. So I'll write A sub phi omega W omega L G. So with complex numbers. Okay, so this is what I mean by has a robust theory of Fourier coefficients. The point here is that, yes. Yes.
If you're not looking at this special holomorphic discrete series, not holomorphic, these discrete series that you're using,
right?
And you had a general function, or maybe you had, I mean, this looks like a multiplicity one Whittaker function statement.
That's correct.
So won't you just then also allow negative coefficients and interpret everything you have as some kind of natural extension? Is there, I understand you maybe the most interesting arithmetic case is when you take these particular discrete series, but is it special to that? Usually these aren't.
So what's I mean,
so these Fourier expansions will have a period meaning, like in Maas's work. So if you're doing this in Abarth plane where you started out, Shimura initially started just with holomorphic stuff, but Maas had done this before with more general guys, right? So
right,
everything makes sense automorphically, and so why the restriction to holomorphic? Is that really relevant in this part?
Well, so
what holomorphic discrete series? I mean,
so the quaternionic discrete series have the appropriate multiplicity one statement for these Fourier coefficients. I think, yeah, for example, if you were to take a generic cusp form on G2, that you don't necessarily get multiplicity one.
Okay.
And so, and I mean, at least in the right, so the construction of these, how it at least goes here is the construction of these quaternionic discrete series is actually defined by in terms of the vanishing of this differential equation. And then we can just use that differential equation to solve the appropriate differential equations that these Fourier coefficients have to satisfy to get these solutions. And then you just sort of check that it's unique. So without that differential equation, the uniqueness.
Well, and if you had a different differential equation, it wouldn't work, you tell me.
Yeah, exactly.
And
right.
how's this related to the, I mean, I haven't looked at this in years, but in the old days, people working on G2 would always say there's this thing that's the analog of a Weyl representation or the oscillator representation.
On the third.
What do you call it? The maximal or minimal? I can't remember what they call it.
So there's a minimal representation.
Yeah.
But that's on for G2. It's strange. You have to go to the threefold cover.
Right, and make an Eisenstein there, and then the residue of the Eisenstein. Right. Those coefficients are not picked up. These are different.
Yeah, so we haven't thought about that case because you would need to work with a totally you'd have to work over a complex
field. Yeah.
Right. And so we wanted to consider cases where the Archimedean types are all totally real. So the threefold cover doesn't fit in that. But in particular, precisely that construction is what we use on the double cover of F4 to construct the minimal thing that'll show up in a few minutes. So that we don't know how to fit that in with G2, but it works for F4. No, thank you very much.
Thanks.
Okay, so it's these constants that are where the arithmetic interest in these modular forms come from, and so Aaron has produced many examples of both cusp forms and non-cuspal modular forms for which these functions here can be somewhat surprisingly, because there isn't a Shimura variety floating around here. These can be normalized so that for at least many examples, these Fourier coefficients are either all rational or can he's even produced examples where they're all integers. And so there's a lot of there's surprising amount of arithmetic content here. And so so with that being said, let me go ahead and explain our extension to the half integral weight case. And so for the sake of time, I'll just point out that what we're going to want to do is we're going to want to take this definition here, and we want to, basically take this precise definition so that I don't have to write it down, where we're working not with integers L, but rather with half integral weight. And there's a couple of different directions for motivation, but let me just go ahead and state what we need to do in order to make that work. So first, let's recall that the maximal compact subgroup here is SU2 cross SU2 mod plus or minus 1. And so, just looking at this, the homotopy type of G2 is determined by its maximal compact. So just covering space theory, you see that there exists up to isomorphism a unique double cover G2 tilde over R, G2 R, that covers the obvious double cover, just modding out by this diagonal plus or minus 2. So I'll call this K tilde. And this group has been constructed and studied for decades at this point in terms of Chevrolet generators and relations. But we're going to want to solve differential equations and write down these explicit Whittaker functions. So one of the first steps we needed to do was to develop a good model for this double cover. And I don't know if this was known. It was definitely not known for me or Aaron, and I am very fond of this. So the statement is that there exists what we'll call a weight 1 linear multiplier system. So I'll write that J lin from G2 R cross its its symmetric space to the vectors, the domain of weight 1 modular form, so recall that's the symmetric square of the standard representation, such that we can construct this double cover by pairs, just like what we saw with the SL2 case. This is, I don't know, I found this very fun. G and G2 are JG from the symmetric space to what I'm going to call V1/2, which is just the standard representation, satisfying that when I compose JG, so I'll evaluate it on X and compose with the symmetric square, and that gives me JLen GX. So it's precisely analogous to what happens for the double cover of SL2R. Namely, we're just taking square root to the appropriate weight 1 multiplier. So using this, we're able to, like, this construction plays a role in the theorem for the Fourier expansions. Okay, so this gives us a cover that we're going to use to define our modular forms on. We also need, so we can now define the notion of a half integral weight modular form, but we need a good notion of level. Something analogous to the theta multiplier system that shows up in the SL2 case. So the problem is, in that case, you use an explicit function. You take the Jacobi theta function and you use it to define a multiplier system. I don't know what the appropriate analog is. As Professor Sarnak's question is, you might hope that there's a minimal automorphic representation on the double cover of G2 that you can sort of use to play the role of Jacobi's theta function. That doesn't seem to exist, or it doesn't exist. There is no minimal automorphic representation on the double cover. So what we're going to do is use, we'll take our double cover over R, over the Archimedean place, and we'll embed it in an Adelic picture and just show that we can talk about, we can embed level subgroups in this way. Sorry, that's an A. So embed this as the Archimedean component of a double cover of the Adelic group. So there's a very robust theory in this context. And one of the key properties of these groups is that the rational subgroup splits the cover canonically. So, excuse me, maybe the second proposition is that there exists a compact open subgroup K1 of 4 inside G2 of the finite Adels, such that, and maybe I'll say and, a splitting S K1 of 4 into this double cover. Okay, and so we really need to work with the local covers here, and in particular, as you might expect, the problem here is really at 2. Like, we need to work out what the appropriate cover is at 2. And so that takes a bit of work, but it's something that can be done. And so this plays the analogous role to the gamma 1 of 4 in SL2. So now what we can do is we can take gamma 1 of 4 to just be the intersection here. So K1 of 4 intersect G to Q. And so this gives me a discrete subgroup of G2R. And by construction, we have, or by these propositions, we have a splitting of this discrete subgroup into the double cover. And so using these two propositions, we can define for L, now an integer, let me say, modular forms of weights L over 2. These will be precisely defined as satisfy the same 4 properties as before, but now they're functions on this double cover, and they take values in sim L of C2 to tensor 1. So in particular, now I can, for example, talk about something of weight 1 valued in the standard representation of SL2. And so these, I need this to satisfy the appropriate 1, 2, 3, and 4. There's again an analogous differential operator that this was defined on the level of the Lie algebra. So passing the double cover, this is not hard. But the point is,
does your first order whatever, I don't know what its order is here in this on G.
It's the first order.
That the product of two functions which obey this will be again give 0.
Yeah.
In other words, if I take one of your forms of half integral weight and square it, will I get something that lives on G that actually is an eigenfunction of your differential operator? Or will it actually be have to decompose into?
So by square, do you mean?
I'm just trying to use. I'm just trying to.
Sure.
My original question was, why are you only sticking to this discrete, special discrete series? Why not an arbitrary function? And one of the advantages of holomorphic forms is that the product of holomorphic forms is holomorphic.
Right. So
it's not true for a mass form. Okay.
So I don't know how general this is true. I should check this, but for example, a weight 1 form, if you compose it with the symmetric square, it does, or a weight 1/2 does be, if you, because you need to compose with the symmetric square or some symmetric power. Yeah, representation. Then you do satisfy the differential equation for a weight 1 form. I haven't checked that in general.
That's good. That really singles out your theory as sort of like holomorphic. Yeah.
Yeah,
because usually the whole point is you have this first order operator rather than something coming that's usually second order from Casimir. Yeah.
Right. Okay, so I'm running a bit short on time, so let me just go ahead and quickly state. So the theorem here is that a similar Fourier expansion principle holds. So namely, again, these I want to expand this with respect to the Heisenberg parabolic, and so the unipotent groups will split canonically in these double covers. So I can still talk about Fourier coefficients. So if I consider an element A, B, C, and D in this symplectic space, which is not positive semi-definite, then again, we have that these vanish. And otherwise, we have something that's a little bit weaker. So there exists a normalized Whittaker function as before. I think I had it the other way around, omega L/2. So now this is a genuine automorphic, genuine function on the double cover, such that the Fourier coefficients of this weight L modular form is times L/2. So this looks exactly like the theorem in the integral weight case, except the caveat is that in the construction, so we use the explicit coordinates of this covering group that I mentioned previously, but we have to take, so this polynomial P omega Z1, we have to at some point take a square root of this. And so in the general theory, there appears to actually be some monodromy that can't be avoided. And so really, this is only well-defined up to a sign. So as a result, up to some arbitrary choice in general. And so you really should think of these as like a plus or minus 1 torsor or something. Okay. But there are actually cases where the Fourier coefficients vanish to the point where you can show that this can be chosen uniformly. All right, so now with, so in particular, this is a good, this extends the integral weight theory well. So now in the last 10 minutes, let me recap the main results and say a bit about the proof. If I have time, and maybe I'll have to punt to questions, so I apologize for that. So let's let R be an order So maybe I should start this off by saying this is a bit of arithmetic invariant theory. So let R be an order in a totally real cubic field, E, which is, and so I need a few definitions. So I'll let delta R inverse be the inverse different. Okay, so definition, a pair, oops, a pain, I mu is balanced. So here I is a fractional R ideal, and mu is an element of E cross that is totally positive. Real quick, why am I saying totally real? So it's not at all obvious here, but this total positivity statement is actually equivalent to if I take the associated cubic ring, modded out P omega Z, or sorry, Y1, and take the associated field of fractions. So this is now a cubic field. So the total positivity of omega is equivalent to E being totally real. That's not, I think, obvious, but that's why we're now dealing with totally real. This positive semi-definiteness. Okay, so a pair is balanced if, so two things. Mu times I squared is contained in the inverse different, and also abound on the norm. So mu, the norm of I squared times the discriminant is equal to 1. So particular, if R, so e.g., if R is maximal as an order in E, then this first condition, so 1 and 2 are equivalent to saying that mu I squared is equal to the inverse. Okay. So now what we'll set is let Q of R be the set of balanced pairs. I mu mod I mu up to sort of the obvious like equivalence relation. So maybe beta inverse squared mu, where beta is some element in E cross. Okay, we're looking at. Okay, and so finally, we say R is even monogenic if it's of the form zy y cubed plus cy squared plus by plus a, where a, b, and c are all even. So this, again, there's these issues at 2, so we have to consider even monogenic in order to say things as cleanly as possible. So, okay, what's the theorem? So what it is that we construct, so there exists a weight 1/2 modular form. So I'll call this theta G2. Such that if, so I'll say two things. If I have the binary cubic, so AU cubed plus b u squared v plus c uv squared plus v cubed. So d is 1, and a, b, and c are all even. Then the p Fourier coefficient of G2 is equal to, this is the statement I said. So again, there's this sign issue, but in this case, it can actually be normalized. So I don't want to say it equals 24 times, well, let me go ahead and write it in general. So the size of QR. So this set of equivalence classes. So what do I need to say now? So if R is maximal, so a maximal order, then QR is a torsor for an obvious group. So A, oh, I'm sorry, there's a fudge factor here. This is 24 times QR. So there's a group for which QR is a torsor that sits in the short exact sequence over the 2 torsion in the narrow class group, and it has totally positive units modulo squares as the kernel. So thus, in this case, the P Fourier coefficient, so P being associated to R in the way as before.
Again, what's E here?
E, sorry, is the field of fractions of R. So let me just write R there. Is equal to plus or minus. So basically, in this maximal case, we can say something more precise about what QR is. So this is 24 times the class number, 2 torsion times. Okay. So there's a couple other families of Fourier coefficients we can say something about, but it's essentially something like this. So I'm not going to, I don't think I have time. So unfortunately, I don't think I have much time to say something about the proof, but let me just, in the last 2 minutes, say, so the idea of the proof. So let's recall what I said about the guy on SL2. I had an SL2 tilde form. There's a weight 1/2 modular form on SL2. That sits inside a dual pair with compact SO3 sitting inside the double cover of SP6. And so here I had my exceptional group here, or sorry, my Eisenstein series of weight 3/2, and here I had this big theta function. So this dual pair sits inside the double cover of F4, and this SL2 sits inside the copy of G2 embedded in F4, which has a, so this is also a dual pair inside the double cover of F4. And so what we do, so we use the automorphic minimal representation. So I'll call this pi min on the double cover of F2. So this was studied recently, and this has been known about for a while, but I don't think anyone worked through the results. So this is in general defined as a residue of a particular Eisenstein series on the double cover, proving that it's a minimal representation is a recent theorem of David Ginsburg. It had been conjectured to be one for probably decades, but Ginsburg proved it. It was published in 2019. So we need a bit more refined work. So we actually study the local components of this automorphic representation, prove that they're minimal, and actually in particular, the Archimedean component, so pi min infinity, we identify with one of these representations constructed by Gross and Wallach. And so that's what relates this, these residues of Eisenstein series to these something similar to the definition I gave for modular, the definition of a modular form. So in particular, once we, and also we need to prove, so maybe prove, maybe I'll say it, compute several, so certain Jacquet modules. We need to study certain Jacquet modules of the local components of this minimal representation in order to prove that there exists a modular form theta on F4 of weight 1/2. In fact, there exists essentially there's a unique line, and if we want to normalize.
Confused. Are you talking about F4 or F2? There's an F2 and there's F4.
I'm very sorry. There's no such thing as F2 here.
Okay.
F4. I apologize. Is that also up there?
Yeah, I was not happy with that.
Yeah, thank you. Right, and so in particular, using the properties of this representation, there exists a unique modular form of weight 1/2 on F4, and the actual arithmetic properties of this in the main theorem, we define theta of G2 as the pullback, so the restriction of this automorphic function on F4 to the embedded copy of the double cover of G2, and it's in analyzing the restrictions of these generalized Whittaker functions we define that the arithmetic invariant theoretic arguments is used to prove the theorem. So I apologize for going a few minutes over, but I'll stop here.
Okay, I guess let's all unmute and thanks Spencer for his wonderful talk.
Thank you.
Questions?
I have a lot of questions, so maybe somebody else ask first. Then I'll maybe then you can end, and then I'll quiz him for a while.
Spencer, I have a question. This is Raghuram here.
Hi, Raghuram.
So you mentioned this, just before you got into the half integral thing, something about arithmetic properties of the Fourier coefficients and there being some examples with Q Fourier coefficients and such things.
Yes.
So, I was wondering, this discrete series, one of the basic properties is that these contribute to cohomology in the middle dimension. And so the question is, if you take one of your modular forms on G2, and if you were to Galois conjugate, take some element in maybe automorphisms of C, or if they live in some number field, some suitable Galois group, and you conjugate the Fourier coefficients, whether you can prove that the conjugated guy is also modular. So is there any statements along those lines that you people have?
This is a good question. So there are certain cases. So I don't know a general answer. I think that's a very interesting question. There are certain cases. So I haven't mentioned cusp forms, but obviously you can just look at cusp forms, although these things are all not cuspidal that I've mentioned. But anyway, in recent work, so if we just consider cuspidal weights L modular forms. So let's say of level 1. So we have this finite dimensional space. So this is finite dimensional, and the dimensions, at least for L, I think I'm not going sufficiently large, but not big. Like maybe it's like greater than 2 or something. The dimensions of these have recently, a formula was given by. So this is recent work of Rahul Dalal, and I want to say 21. And he uses the stable trace formula on G2 in order to do this. It's actually a very beautiful argument. And so the only thing I can say is that there are specific examples where looking at this formula, you can see that, for example, I think at weights, either 6 or 18, I don't remember, this is one dimensional. And so in particular, in that case, you should be able to extract some Galois conjugate statement without explicitly computing anything. But beyond that, I don't know what the relationship is with the differential equation, because I guess it would depend. Yeah, I'm not sure beyond that.
By the way, this weight 6 thing that's unique should be the Saito-Kurokawa thing along the long root parabolic, corresponding to the modular form delta.
Yes, right. Yes, yes. So is weight. So okay, I have to think about the weights there. But
yeah, no, it should be 12/2 is the quaternionic weight.
Cool.
Yeah.
So I'm not sure if I've answered your question, Robert, but
no, yeah, I was just, it's kind of open-ended. I was just wondering what might be known, and this is
I don't think much is known, but I think it's a really interesting question worth thinking about.
Yeah, I mean, these kind of automorphic forms you're constructing should be contributing to the cohomology of a locally symmetric space for G2 with coefficients in some suitable local system coming from a finite dimensional representation capturing that your parameter L. There is a finite dimensional representation which goes hand in hand with your quaternionic discrete series, and that will give you a local system on that locally symmetric space. And in those cohomology groups, one would expect to see these kind of automorphic forms, not the half integral weight ones, the one
sure
before. Yeah.
By the way, the relevant weight here is the highest weight of the local system is you take L over 2, where L is the weight, and you multiply by the highest the long dominant root. Just by the way.
Yeah. Thank you.
Yeah, very nice.
Okay, I guess that ends the recording, and if you have more questions, you can stay here and chat.